We want to continue our discussion of predicting solubility for molecular compounds. The idea of like dissolves like becomes even more important when we're looking at covalent compounds because now we have some variety. All ionic compounds only dissolved in polar things. Well, now when we're dealing with molecules, we can have polar or nonpolar molecules, and especially we can have polar or nonpolar solvents. And so as a result, we need to, in order to predict solubility, we're going to need to predict the polarity of both the solvent and the solute. So for example, water is polar. Remember, we want to remember that one. So it's going to be capable of dissolving other polar things like methanol and sugar, but not benzene or carbon tetrachloride. Since those are nonpolar, we would not predict them to dissolve in water, and they don't dissolve in water. When we look at two of those, sucrose, so that's sugar, and benzene, C6H6, if we look at these are their three-dimensional structures of the molecules, we also have the formulas. We can think about how we would predict whether or not they're soluble in water. And if we think about this sucrose molecule, this thing is extremely irregular, right? There's a lot of oxygen bonds. There's a lot of oxygen in there. Those oxygen are the red spheres, and we can see, for example, right here, it's bonded to a hydrogen. So sucrose is capable of forming hydrogen bonds, which is the same thing as water can do. So that's another type of like interaction. These highly polar, you don't remember for nonpolar, you need symmetry. You need bonds to cancel each other out. In this case, there's nothing canceling anything out. So this is a very polar molecule, and it's very soluble in water. When we look at benzene, the structure, it has the idea that you have, say, a pull this direction, but you also have a pull in the opposite direction, and those cancel each other out. This is very nonpolar. It only interacts via dispersion. It does not interact via dipole-dipole or hydrogen bonds. So as a result, we'd expect it to be very insoluble in water, which it is. We can also tell based on the fact that it's C6H6. C6H6, only carbon and hydrogen, means this is a nonpolar molecule. It is all nonpolar molecules we expect to not be soluble in water. And if we think about the why of this idea, it's the same that we saw before with ions. When we have ions dissolved in water, they are fully charged. And so polar solvents are able to interact attractively with those ions. Right? The polar solvents in the case of water has the positive end and the negative end. The water molecules can arrange around the ions in a hydration shell, and that allows for interactions that are attractive. You can think it literally is pulling those ions out of the solid and dissolving them. The same thing happens for a polar molecule that's going to dissolve in water. For example, methanol here. If you're going to dissolve that in water, methanol is polar, so it will be able to interact with water via dipole-dipole interactions, which are attractive. On top of that, in the case of methanol, we can see that it can form hydrogen bonds. Because it has the OH, it can still form hydrogen bonds. That's a local interaction of those atoms in the molecule. So even though they're different types of molecules, they can still form hydrogen bonds that are strong. So most molecules that can form hydrogen bonds are very, very soluble in water because they're forming the same types of interactions with water. They're forming attractive interactions, the kind of things that would tend to lead to dissolution, to lead to mixing. They can mix and still form attractive interactions. And so this is really the motivation for why things do mix. And so if we want to think about what happens if we try to, say, make a solution from things that have different. So if we have, say, bromine, we've seen that is something where the bromine, those are, say, a nonpolar molecule because it's two bromine atoms. And iodine chloride is a polar because it's two different types of atoms. So bromine, same atom, same two atoms. Iodine chloride is two different atoms. And so if we keep them heterogeneous, that would be something like this, where they are divided, right? We'd have a region of bromine and a region of iodine chloride. That would be distinct from a homogeneous or a solution where they are all mixed together. And because these have different types of polarity, we would expect this mixing doesn't happen. The real reason for this is because in order to mix, you would have to break the dipole-dipole interactions that exist between the iodine chloride molecules. Passively, molecules do tend to mix. We'll come back to this later on in the course, but you know, just like your room tends to get dirty, your house tends to get messy, molecules have a tendency to just get mixed up together. But in the case of this, the bromine molecules are more than happy, right? Because they're interacting. This is all just dispersion interactions. But in the case of iodine chloride, there are dipole-dipole interactions that are happening between all of these molecules. And when they have this kind of heterogeneous clump, the bromine stays on one side, the iodine chloride stays on one side. But if they all start to mix together, this iodine chloride now has broken those interactions. Instead, it's having to interact with these bromine via dispersion, which is a weaker interaction. And so these polar molecules do not want to mix with non-polar molecules, because that would lead to breaking dipole-dipole interactions, which is not favorable, and you're not forming any new interactions. If it's two polar molecules, they can just form new dipole-dipole interactions. So it's a favorable attraction, so the mixing can happen. You do not break dipole-dipoles if you're not going to form some new attractive interaction. So what we want to be able to do then is take a look at a molecular formula and make a prediction. Is this compound soluble in a given solvent? And in this case, I want to know if it's water. So I got CH3, CH2OH, CH4, CH3, CH2, CH2, CH3, and C6H12O6. So ethanol, methane, butane, and glucose. So if I'm trying to figure out whether or not something is soluble in water. And so when we're predicting solubility, especially these aren't ionic. All of these start with carbon. Carbon is a nonmetal. These are all molecular or covalent compounds. And so that means I don't use solubility rules. I'm reliant entirely on like dissolves like. So what's the solubility of water? Well, water is polar. So in order for a compound to be soluble in water, I'm really just asking, are these compounds polar? That's really all I'm asking for here. And if it's polar, then yes, I would predict it to be soluble. Not polar, no, it's probably not soluble. There are fringe cases. If you go look, you can find things that we classify as polar that aren't soluble and everything. We're not going to worry about that. I'm not going to ask you about those fringe cases. I'm going to ask you about things that are very clearly one way or the other, and that's what we're going to focus in on, is predicting those trends and following those trends. So first one, CH3, CH2OH. We know this is an organic compound. You'll note all of these are organic. There's lots of carbon. And what we want to focus in on is this OH. That's in the condensed formula. We know that if we wrote out the molecular formula for ethanol, we'd have this OH. That can form hydrogen bonds. This thing is very polar. This is very soluble in water. You can just keep pouring in the ethanol and it will stay soluble. So this is the alcohol that's in, say, like most drinking alcohol, not most, all drinking alcohols, grain alcohol commonly described. And so this is very soluble in water. You can just keep mixing it in. There's no limit to how much you put in. If we look at CH4, in this case, we only have carbon and hydrogen. If we look at the Lewis structure, we could also say, hey, there's no lone pairs on that carbon atom. All the outer atoms are the same. That is nonpolar, so that is insoluble in water. Also, if we only see carbon and hydrogen in the molecular formula, that's a nonpolar compound. So hydrocarbons, only carbon and hydrogen in the compound, not soluble in water. Along that vein, CH3, CH2, CH2, CH3, that's a fancier way to write it. Still only carbon and hydrogen, that's insoluble. Again, when you have only carbon and hydrogen, we can see those bonds are all spread out. They end up canceling each other out, all the different bond dipoles, and that is going to be a nonpolar compound. Bond dipoles are already really weak, then they cancel each other out. That is a very nonpolar molecule. Butane is not soluble in water. When we see C6H12O6, it's not written in a condensed formula, so we would maybe have a little bit more trouble. But when we see there is this many oxygens. I have as many oxygens as there are carbon atoms in the molecule. That is a lot of oxygen. That is very polar probably, and we would predict it's polar. If we look at the shape, we can see that is definitely the case. Again, there's no balance. There's nothing to balance out those oxygens. We can also see that there is explicitly, again, the red oxygens are bonded to hydrogens. This thing can form hydrogen bonds. This thing is soluble. Glucose is a type of sugar. Sugars are characterized by these OHs. So they are all tend to be very soluble. And so we can see that there. And so this one of the things we can start to see is we make these classifications for compounds. For example, we have the word hydrocarbons, things that only contain carbon and hydrogen. One of the reasons we have that is it imparts some of their properties. So you can just kind of know hydrocarbons are always nonpolar and not soluble in water. Sugars have a bunch of these OHs, oxygens bonded to hydrogens. They're all very polar and very soluble in water. Participation 9.4, question 3. Determine whether each of the following compounds is soluble in water. A, CH3OH, B, C10H22. Is the third question on participation 9.4, due Friday, September 4th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, determine whether each of the following compounds is soluble in water. It's CH3OH and C10H22. When you start dealing with molecular compounds, you also tend to start dealing with a lot more liquids. And so we have some different language for solubility when we're dealing with liquids. And the words we use are miscible and immiscible. And so miscible means liquids that form a solution. So miscible, it literally is similar to like mixable. So if we think of like the words literally like mixable, like they can be mixed together. Whereas immiscible, that I means not. So not mixable. And so miscible liquids do form a solution. So immiscible liquids, that would be something like oil and water. If you have oil, that is a very nonpolar. Oil is generally almost entirely hydrocarbons. And so you have very nonpolar, that is not going to be soluble with water. So they separate out into different layers. So immiscible liquids form distinct layers. So if you were to say pour oil into water, you get that separation of the two layers. You can see the differences. This isn't soluble, so it is heterogeneous. So it is a heterogeneous mixture when you mix oil and water together, but it is not homogeneous. One of the reasons for the differences in the language, especially miscible, is, for example, ethanol and water. If you put a lot of ethanol into water, the ethanol becomes the solvent just by nature of there being a lot of ethanol. But if you have a lot of water, that's the solvent. So when you have two liquids that do mix, it's hard to tell which one is soluble. So we just say that they are miscible together. Either of those liquids can be the solvent if there's more of it, but they both will just mix together and form a homogeneous mixture. So that's the motivation for having this slightly different language here. Also, specifically, when we're talking about dissolving things into water, we have some language of hydrophobic and hydrophilic. So literally, hydrophobic means water fearing. So hydro means water and phobic, like phobia, like claustrophobia. You're afraid of close, small spaces. Molecules that are hydrophobic are considered to be afraid of water. So they avoid water. They do not dissolve in water. So hydrophobic molecules are not soluble in water. Water is important enough that we just have this classification, this word for not being soluble. One of the other, and hydrophilic then means water loving. So like Philadelphia is the city of brotherly love. Phila literally means love in Greek. So hydrophilic is water loving. These are compounds that are soluble in water. So these are overall designations. Anything that is soluble in water, we would say is hydrophilic. These are kind of adjectives that we can start to apply to kind of like parts of molecules as we see moving forward. But these also are really common in a biological context. that different parts of different molecules, different parts of molecules in living things would be considered either tending to dissolve or tending not to dissolve. And there can be molecules that kind of get a mix where there's some friction there, and we'll see how that can play out. Okay, we're over halfway through, and we have found 3 questions for participation 9-4. I don't think we're going to keep up that pace, but who knows? Got to keep watching the videos to find out. I'll see you in the next one.